Hi. This chapter, set theory, or this subject set theory, is very important and it is also very fundamental. What is a set? Set is a collection of distinct elements. Okay. So consider anywhere where you have different elements that are distinct, you can think of it, all of those elements, and you can fit it into one place. Okay. Then you name it. That is a set. So you are just concerned with the elements. You are just concerned with the distinct elements, and not in the order that you are collecting them. So this is what a set is. A set is a collection of distinct elements. For example, think about university. In the context of university, all students are distinct. Okay, so you can just put all of the students into one entity and call it a set of students. You want to pet a cat, and you go to a shop, and you ask the shopkeeper, what are the different breeds of cats. Now each breed is distinct, and because all of the breeds are distinct, then you put them into one entity called as breeds of cats, and in it each element is nothing but the different breed of cats. And set is very important, because building upon set theory, other concepts are derived. For example, the counting principles. Okay, in combinatorics we will see that in combinatorics we are looking to find out the ways of doing things, in what ways, in how many ways you can achieve this operation, achieve this task. There also, each way is one distinct element. Each way is one distinct element. Let's say you have to perform two tasks, task 1 and task 2. And if you perform both the tasks, if you perform both the tasks, task 1 and task 2, then your objective is supposed to be fulfilled. Now there is a set which includes the ways to perform task 1, and then there is another set which includes, which every element of it is the ways to perform task 2. And we will see in the combinatorics that the total number of ways to perform, to achieve your objective, is going to be the number of elements in task A in task 1 multiplied by number of elements in task 2. Actually, this is very basic fundamental principle of counting, and this is mostly, it is very commonsensical also. But you will see that the set theory is the base for all of those. Even in computer science, in the subjects of theory of computation, entire theory of computation is a set membership problem. When I will start theory of computation, you will see that a language is a set of strings, and the whole of theory of computation almost is nothing but you are given a word, and you have to find out whether this word belongs to the language or not. What it really means is that whether this word is an element of this language, where language is a set. So in combinatorics is built upon set theory. In your theory of computation, because set is very fundamental. Set is just a collection of distinct elements. Like I've given you many examples. Everywhere where you find a distinct elements, and you are not and their order is not your concern, that which element should be kept first, which element should be kept second, in what order is not a factor. Then all of then the collection of such distinct element is a set. So a set is a unordered collection of distinct elements. Unordered collection of distinct elements. Distinct elements. When I was working in an office, I used to work on Java, and there was a interface or parent class called as collection. There's something to do with sets. So even if you give the repeated values, when you call that class, which is basically a set, it will return the elements with unique values. Means even if you give the set values to be 1, 2, 3, 3, if you give, let's say, a is equal to 1, 2, 3, 3, 4, right? So even then, when you it will return a to b, it will always return a to b 1, 2, and 3, 1, 2, 3, and 4. So even if any element is coming more than once in set, we are only dealing with distinct elements. So duplicates are not allowed. Duplicates are just ignored. Okay. So cardinality of A. What is cardinality of a set? Cardinality of the set is number of elements in the set. So cardinality of A is cardinality is represented like this. So this means cardinality of the set, which is equal to number of elements in the set. So cardinality of A is 4. Okay, cardinality of A is 4. And what are the elements of A? 1 is an element, 1 belongs to A, 2 belongs to A, 3 belongs to A, and 4 belongs to A. So because these are 4 elements, so cardinality is 4. Okay. So let's take only 1, 2, 3, 4. Let's take 1, 2, 3. Set is an unordered collection. Unordered collection. So we are just concerned with this distinct elements. So any other set, let's say if I take another set, any set with the same elements, 1, 2, 3 only, B is 3, 2, 1, and any other set, C is 2, 1, and 3. Then all of these are equal sets mutually. A is equal to B, A is equal to C, B is equal to C, B is equal to A. So I was talking about that class in Java, which is a set. So what happens is every time that you call a set, it will return the elements, same elements, but their order may not be same. Every time the set is called, then what it returns is a set with same elements, but the order can be changed because order is irrelevant. We are not concerned with the order in which we are collecting the elements, like what element is to be collected first, or what is second element, what is third element. So instead, we don't talk like that. That what is the first element of a set, what is the second element of a set. It's just what are the elements of set. This is not an array. Array is an ordered collection of okay, later on, but array is an ordered collection of similar data types. Leave it. So all of these elements are same. A is equal to B. This is about the equality of two sets. Two sets are equal if their elements are same. If they have same elements, then both sets are equal. What is a subset of a set? What is a subset? So we are concerned with set A right now. So what is a subset of set A? If there is any other set whose elements are from set A, what does it mean? It means that a set B is said to be a subset of set A. A set B is said to be a subset of set A if all the elements of B, all the elements of B is also an element of A. Is also an element of A. So take two sets. B is equal to 2, 3, and C is equal to 3, 5. Now, out of these two sets, B is the subset of A, but C is not a subset of A. B is a subset of A, and C is not a subset. C is not a subset of A. Why? Because all the elements of B, which is 2 and 3, all of the elements of B is also in A, or the elements of B are from set A only. But elements of C are not from set A alone, because C contains 5, which is not which is not an element of A. So 5 belongs to C. This is the symbol to represent. So on this side, this is the element. Okay, and this is your set. So belong symbol means that this element belongs to this set, or this is the element of this set. So 5 belongs to C. Okay. But 5 does not belongs to A. So there is at least one element in C that is not from A. So C is not a subset of A. Okay. If a set is given to you and you are asked to form a subset from this set, so you know that the elements for a subset has to come from A only. Has to come from A only. And from the definition of a subset, the set A is a subset of itself. From the definition of subset, if all the elements of B, if all the elements of B is also an element of A, so definitely all the elements of A is an element of A. So every set is a subset of itself. Every set is a subset of itself. So every set is a subset of itself. Now, how do you form a subset? If a set is given to you, like A is given to me, and if I have to form a subset of A, how can I do that? So it is clear that the elements of that subset is going to come from A only. Is going to come from A only. So how can we form a subset? For every element, I have two choices. That in my subset, whether I will include this element or not. I may in my subset, I may include one or I may not include one. Okay, let's say I don't include one, but I include 2 and 3. Then this is what that subset is. So you can say that B is formed. How B is formed? Because I had two choices for every element. If I choose all of the element, then I get the set itself. And that is what it is. Every set is a subset of itself. I don't choose one. Every element has two choices. So for one, I am not choosing it to be a part of my subset. But other elements, 2 and 3, is a part of my subset. So B is a set which happens to be a subset of A. So let me write all possible subsets of A. So elements of A is 1, 2, 3. Okay. Now I know one of the subset is the set itself, and that is when we choose all of the element to be an element in my subset. If I choose every element of A to be an element of my subset, then what we get is this set 1, 2, and 3, and this is nothing but the set itself. So this is one of the subset. This is trivial subset. One of the trivial subset of a set is the set itself. That is when we choose every element to be in my subset, to be an element in my subset. Now, let me choose the elements, let me choose the subsets of cardinality 2. So the cardinality of the subset is going to be from 0 to 3. The length, the cardinality of A is 3, and my subset, the elements of my subset can be from set A only. So the maximum length of my subset will be 3. That is when the subset is the set itself. And for any other subset, what I'm going to do, either I'm going to pick 2 elements and not pick 1 element, or I'm going to pick 1 element or not pick 2 elements, or I'm going to not pick any of the element, because for every element I have 2 choice. So let me write possible subsets of cardinality 2. So for cardinality 2, for every combination, so if for every combination I am getting 1 subset. So let's say for cardinality 2, I have to select 2 elements in my set. I have to select 2 elements in my set, right? Let's say I don't select 1. If I don't select 1, and then I will select 2 and 3, and this set is 2, 3. Similarly, one another possibility is that I don't select 2. If I don't select 2, then my set, I get another subset which is 1 and 3. So as you can see, to form a subset, for every element of A, you have 2 choices. Either this element is in your subset, or this element is not in your subset. And because of this, you are getting different combination. In this combination, all 1, 2, 3 is in your subset. In this combination, 1 is not in your subset, 2 and 3 is in your subset. So in this way, how many combinations you will get? This is very much like 1, 2, 3 is very much like Boolean table with 3 Boolean variables, and every variable can take value 0 or 1. So number of combinations possible is going to be 2 power 3. So here it is number of subsets possible for this set A is going to be 2 to the power 3. This time I will choose 1 and 2, and I will not choose 3. So my subset is 1 and 2. So these are all the subsets of cardinality 2. Now I will choose all possible subsets of cardinality 1. How can we do that? So for 2 elements, I'm not going to make it a part of my subset, and for 1 element, I'm going to put it in my subset. So in how many ways can you make the cardinality 1? So every time I'm just going to select 1. So let me select 1, then 2 and 3 I'm not selecting. I'm not selecting it to be my to be an element in my subset. So this is my subset. Then I'm selecting 2. Then I'm selecting 3. Now there is one more type of set. There's okay. I've not discussed the types of sets, but there's one type of set which is called as empty set. Empty set is okay. How a set is represented? A set is represented by curly braces with elements with all the elements separated by commas. So the elements of A is 1, 2, and 3. So it is enclosed between the elements of the set is enclosed between 2 curly braces, and they are separated by commas. So if a set does not have any element, then you write it like this. What does it mean? That this is a set. No doubt this is a set, but it has no element. Okay, that's what a empty set is. A set, it is a set, but no element. And it is also it is also represented as phi. So what phi is? Phi is equal to empty set. So one of the possible combination is that you don't select any of the element to be in your subset. So and that is your phi, or this. So total number of subsets of set A is 8. There are 8 total subsets. These two, this and this, they are called trivial subsets. For every set, the set itself and the empty set, they are the trivial subsets of a set. Empty set is a subset of any set. Okay. For any given set, the set and the empty set, these two are trivial subsets of a set. Trivial subset. And remaining, so these two are trivial and remaining are subsets. One more thing, there is something called as proper subset. So what is a proper subset? Proper subset is a subset of set that is not the set itself. Or in a proper subset, you have the cardinality of proper subset has to be less than the cardinality of the set, or there is at least one element, and this is the real definition. A proper set subset of a set is when there is at least one element in the set which is not there in subset. So apart from this, for every other subset, there you can find at least one element which is in A but not in the subset. Like for this example, 1 is not a part of the subset, or 2 is not for this subset, 3 is not in this subset, 2 and 3 is not present in this subset, 1 and 3 is not present in this subset, 1 and 2 is not present in this subset. None of the element is present in this subset. So all of these subsets are proper subset. And for proper subset, how do we represent proper subset? For example, let's say this is my set B. B is equal to 2 and 3. Then how do I represent that this is a proper subset? The symbol for proper subset is this, so that B is a proper subset of A. Okay, so it is also a subset, so you can write, let's say if this is C, then you can write C is a subset of A, but C is also a subset of A. This is true also, and this is true also. Okay, but in this case, this is only a subset of A. This is only a subset of A. This 1, 2, 3, this is not a proper subset. This is not a proper subset, but this is a subset. Okay. So as you can see that for a given set of length 3, the total number of subsets possible is 8. If the size of the set is n, if the cardinality of the set is n, then what is the total number of subsets possible? It is going to be 2 to the power n, because then how many combinations are possible? 2 to the power n. Okay. So if the cardinality of A is n, the number of possible subsets of A, number of possible subsets of A is equal to 2 to the power n. What is power set of A? What is a power set of A? Power set is a set of all the subsets of A. All the subsets of A. So what is the power set of A? Power set of A is going to be equal to all of this. Means power set of A, in the power set, each element is a set. So set can have a set as an element. So it is possible. It means, of course, yes, it has to be distinct element. Set can have anything in as its element, anything. So not numbers. Like in the introductory video, student 1 is a set. Can be one element. Student 2 can be another element in a set of the students. What is the power set of A? Power set of A is 1, 2, 3. 2 3, 1 3, 1 2, 1 2 3 and 5. So this set is a power set of A. So if the cardinality of A is n, then what is the cardinality of power set of A? If cardinality of A is n, then what is the cardinality of the power set of A? This is equal to 2 to the power n, because there are 2 to the power n elements. There are 2 to the power n subsets of a set. So each subset is an element of power set. So the cardinality of power set is 2 to the power n. This is trivial subset. This is trivial subset. Now you can say that this is one of the representation of set. This is how one of the way to represent a set is you have a curly braces and that encompasses all the elements which are separated by commas. There's another representation of set. You can represent set using a statement of English language that is called set builder notation. So that statement itself encompasses all the elements, all the possible elements. How? For example, in this case, A is equal to 1 2 3. I can write in English statement something like A is equal to X, such that X belongs to natural number and X is less than 4. Then this is nothing but this. This n is also a set of natural numbers. N is set of natural numbers. So this is the example where number of elements is 3. But there are the sets can be finite set or it can be an infinite set. Some of the very popular infinite set, one of them is natural number, set of natural number. So which is n is set of natural numbers. Similarly, z set of all integers, q set of all rational numbers, r set of all real numbers. These are some of the popular infinite sets. Okay, what is the significance of set and subset? What is the significance of it? All of the subsets of this set A are nothing but set in themselves. They are the elements has to be decided from A. So it's like the world of A. So it is, in other way, you can understand this as that in the world of A, these are all possible sets that can be. In the world of A, this is the all possible sets that can be. For example, take the case of university. In university, you can have one set of students. Some students may be learning physics. Some students may have opt to learn chemistry. Some may have opt to learn mathematics. Some may have opt to learn about politics. Okay, so every set. So all the other sets, means a student who learn physics, they are going to be, the elements of these sets are going to be from the elements of set of students only. So set of students is like a universal set, and every other set in the context of university is a subset to this universal set. So likewise, in this case, A is a universal set. So universal set, A is a universal set, and every other set in the world of A, every other set is a subset to this A, because every other set, the elements will come from A only. Similarly, in case of university, for every other set, like physics students, set of chemistry students, set of politics students, set of English students, their elements are going to come from set of students only. Now, it might happen that, let's say, there is one subject where every student is learning that subject. For example, English literature. Everyone is learning that English language. Then, in this case, this subset is the set itself. Like this is the scenario of this, that that every set is a subset of itself. Similarly, there must be some subject where teachers just come to the classroom, but there is no one because nobody has opted to study that subject. Teachers just getting the salary, and the classroom is vacant. What can that subject be? What can that subject be? Let's say history. Let's say it's a college name is University of Science, but there is a history subject also, and there's also a history teacher in it, but nobody is interested in studying history. So in the set, so there is a set, that a set of history students or students of history. So there is a set, but there's no element in it. That is what is empty set is. Okay. So this is the significance of about set and subset. So what is a universal set? A universal set is a set that is a superset to every other set. So if for a given context, there is one universal context of city population. What is the universal set? It's the set of all people in the city, and set of men, set of women. These are the subsets. So men or women, in these subsets, the element has to come from this universal set, which is the set of all people. So this is what it is. There's another representation of set. Right? I talked about this is one representation, curly braces, and inside of the curly braces you write every other element with a means separated by commas. The other notation is set builder notation, and there's another pictorial representation which is called as Venn diagram. In the next video, we will learn about set operations. So most of the set operations or the next video maybe will be properties of sets. All of them are very self-intuitive. Self-intuitive means you look at the property and you are like, obviously it has to be like that. And even for some properties where you don't get that obvious feeling, those properties can easily be visualized using Venn diagram. So maybe not in this video. In the next video, I will first start with Venn diagram, and then I will also cover set operations. Thank you very much. Hi. Now we will look into different set operations like union, intersection, set difference, symmetric difference, and complement. Um, some of these operators are binary operators, except one, which is complement. Complement is a unary operator, means the operator that is going to be applied on a single set. But other operators like intersection operator or union operator or set difference or symmetric difference, they are binary because they are applied on two different sets. So you can think of it in this manner. Op is the operator that can either be union or intersection or set difference or symmetric difference. So this op is an operation or operator that can be either union. This is a symbol for union. This is a symbol for intersection, union intersection. This is the symbol for set difference. This is a symbol for symmetric difference. Okay. And the two operands, the left operand and the right operand, they are going to be sets. So this is operand 1 and operand 2. So left operand 1 and operand 2. So op 1 and op 2, they are sets. Op 1 is a set and op 2 is also a set. They are sets. Operands is set and the operations are set operations. Set operations being applied to two sets. Now, what are these operations, different operations? That's what we are going to see one by one. Okay, let's start with intersection first. These are two sets, A and B. Okay, and intersection means that it will return a set that will have elements which belongs to this region. Means if you have set A and set B, the intersection of set A and set B means that you have all the elements that are in both A and B. So such that X not only belongs to A, but it has to belong to B also. Means that A intersection B, when you apply the intersection operation between two sets A and B, then this whole thing will give you a set, or this whole thing is a set. The set operation, when it is applied between two sets, the ultimate result is that of a set. So A intersection B is a set, and the elements of this set are the common elements of A and B. Okay, so A intersection B, the elements are elements of this set. Elements of this set are the common elements, of A and B. Common elements of A and B. Okay. For example, if A is, let's say, 1, 2, 3, 4, 5, and B is, let's say, 3, 5, 7, 9, then what is the set A intersection B? A intersection B is a set, the elements of which are the common elements of A and B. What are the common elements between A and B? 3 is present in both sets, 3 is an element in both sets, 5 is an element in both sets. So A intersection B is 3 and 5. 3 and 5. If you just see any arbitrary two sets, this is how you represent two arbitrary sets. And all of these different set operations, whether it's intersection or union or set difference or XOR, symmetric difference, all of these different set operations are actually giving you some region from the Venn diagram. Just look at this. Okay, I will show union here. So let me just draw an arbitrary two sets here. So you can see how many different regions, because of these two sets, how many different regions are possible. One of the possible region is this region, which is the common portion. And for to get this element, all these elements, you have intersection operation. So your intersection operation will return a set that has all the elements in this region. Okay. Similarly, all other set operations will give you some of the region from this diagram. The union operation, which is the second operation that we will study. So second operation is union operation. So union operation will return you what area of the means elements from which region, everything. Intersection gives you this portion, right? Intersection gives you this portion, the common region. Union will give you all the elements that is in A or it is in B. It will just return everything. Okay, so what is a union? A union B. A union B. This is equal to all the elements X such that X belongs to A or X belongs to B. So think of this. If your set A contains n elements and set B contains m elements, okay, and they happen to be disjoint sets, means there is no sharing area. Okay, let me draw a disjoint set. If the number of elements in A is equal to m and number of elements in B is equal to n, then what is the number of elements of A union B? A union B will have all of it. All of it. So the number of elements in A union B is equal to m plus n. This is in case of disjoint sets. in case the sets are not disjoint, which is this arbitrary sets we are taking, what will happen? Let me take one example and show you. Let's say A is 1, 2, 3, 4, 5, 6, and B is 5, 6, 7, 8. Okay, then what will be A union B? A union B means every element from A and B. So you can just directly write the elements of A and B. Of course, the order does not matter. So you can reshuffle if you want, but the elements are from A and B. But if you just straight away take the elements of A and straight away takes the elements of B, 5 and 6 are going to be written twice because they are common elements. So when you are listing all the elements of A, one time you will write 5 and 6, and when you are listing all the elements of B, second time you will write 5 and 6. So 5 and 6 will be written twice. Okay, and duplicates are not allowed. So let's say you will write all the elements of A, 1, 2, 3, 4, 5, 6, and then all the elements of B, 5, 6, 7, 8. Of course, when you are writing your set in this manner, you will correct yourself. You are not going to write 5, 6 twice because duplicates are not allowed in sets. Means duplicates are ignored in sets. Okay, but you cannot say that the number of elements in A union B for this case, in case when the two sets have some elements in common, they are not disjoint sets. You cannot directly say that this is equal to this is equal to number of elements in A plus number of elements in B, because that will be wrong. Uh, you can write this. You can say this in case of disjoint sets, because in disjoint sets saying this is akin to just listing elements of A and elements of B without taking care if any element is coming twice because of the common element. So this goes fine in case of disjoint sets because there is no common element. When you list all the elements of A, then when you list elements of B, no element is going to come twice because there is no shared elements. There is no common elements. So in this case, this does not hold actually. So in number of elements in A union B is how much? Is going to be 8. You can see for yourself number of elements in A union B is 1, 2, 3, 8. This is equal to 8. But what is the number of element in A? 6. And what is the number of element in B? 4. So 6 plus 4 has to be 10. So the correct formula in case of A union B to find the cardinality of A union B set is number of element in A plus number of element in B. Then I am going to subtract. Then I am going to subtract number of elements in A intersection B. When you subtract it one time, so what happens? I want everything, right? A and B. I want everything. I want everything. So while listing all the elements of A, you have included these elements. Okay. Now you want every element of B also. Every element of B also. So far good. But now again you did this because these are elements of B also. So you are counting this twice. So because you are writing it twice, or when you are calculating the number of elements, you are counting it twice. That's why I have subtracted with A intersection number of elements in this region. I have subtracted that so as to not count the same element, the common element twice. And this formula is called as inclusion exclusion principle. This is principle of inclusion and exclusion. Inclusion exclusion principle. So this is inclusion exclusion principle. Now I told you about the Venn diagram. So in this Venn diagram, this is about two arbitrary sets. Any two arbitrary sets, that's how it is represented by two circles, and there's going to be one intersection part. But these are the Venn diagram for two sets which are disjoint. From the arbitrary sets, you will come to the solutions. From the arbitrary sets, you will come to the solution. Here also, from the arbitrary sets, I come to this solution. This is a general result, because in case of this disjoint sets, the number of elements in A intersection B will become zero. So this becomes this only. This becomes this only. So this is the general result. Okay, holds for all times. So when it becomes disjoint, then this term is zero. So for a general result, to get a general system, you take two arbitrary sets to get to a general outcome, or so as to get to a um, general result, you use the arbitrary two sets in this manner, and not you don't take these special cases. Like this is one special case where A is a subset to B. These are the special cases. For these special cases, you just fit that special part. Like in this case, A is a subset of B. Then A union B is nothing but B. When A is a subset of B, then A union B is B. Then what is the number of element in A union B? It has to be number of element in B, right? See if this formula holds for that or not. The number of elements in A union B is equal to number of element in A. Okay, no problem. Plus number of element in B minus number of element in A intersection B. And number of element in A intersection B is the entire A. So this becomes number of element in A plus number of element in B minus number of element in A, which is nothing but number of element in B. That's why whenever if you want to come to a solution using Venn diagram, you use these two sets. This is how you will draw two arbitrary sets in Venn diagram. Every set operation will give you elements from some region. You know what intersection will give? You have seen that. What union will give? It will give every elements. Now A minus B. A minus B. It will give those part of A, those elements of A. It will give this region. Those elements of A apart from those elements which are common with B. So A minus B will give you A minus something. So you are not going to return all the elements of A. Some elements of A you are going to remove. If this is your operator, which is minus, and left operand is A, then A minus means that those elements of A are going to be removed that is present in this set, that is present in B. Okay. If this is your two arbitrary sets A and B, then A minus B is this portion. Similarly, what will be B minus A? This portion. Okay. So B minus A is equal to, from the set B, you don't want to include those elements that are in A. So from the set B, from this whole set B, you don't want to include this part. So X such that X belongs to B, and X does not belongs to A. This is your set difference. Next is symmetric difference. Thank you. Now in this video, let's look at the product of sets. So what is the product of two sets A and B? Let's say you have two sets a set A and a set B. Then what is A cross B? So we have seen different set operations like union, intersection, set difference, set symmetric difference between two sets, and the result of it is also a set. This is also one of the operation, set operation, and the result of this set operation is also a set. Okay, a set is an unordered collection, but the result of it is also an unordered collection, but unordered collection of ordered pairs. So this is a very important point. So A cross B will give you set, no doubt set, which is an unordered collection. So set of all possible ordered pairs. Set of all possible ordered pairs. Okay. So what do I mean by this ordered pairs? What is this ordered pair? Okay. Like let's say if A is 1, 2, and 3, and let's take B to be A, B, C. Then what is ordered pair? Means that this is equal to a set. This is a set which is each element of it is a pair. Each element is a pair of element. Means each element is a pair x and y, where x belongs to A and y belongs to B. Okay, such that x belongs to A and y belongs to B. So for every A, what are the ordered pairs possible between A and B? 1 and A, 1 and B, 1 and C. Because for every A, it will come, each element of A will come with each element of B. With the in this ordered pair, why it is called ordered pair? Because the first element of this pair has to be from set A, and the second element of this pair has to be from set B. So this pair is ordered pair, but because this is a set of ordered pairs, so okay, let me first write all of the possible ordered pairs. Okay, so all possible ordered pairs is 1 and A, 1 and B, 1 and C, 2 and A, 2 and B, 2 and C, 3 and A, 3 and B, 3 and C, right? So with A, A has to be paired with each element of B. So you have this. Similarly, 2 is also an element of A, and each element of A has to be paired with every element of B. So 2 will be paired with A, 2 will be paired with B, and 2 will be paired with C. That's what this is. And similarly, 3 will be paired with A, B, and C, and that's what this is. Okay. So a set A cross B set will be equal to all of these elements. And because it's a set, the order is not important. So each element is an ordered pair, but there is no order of the, it means each element is an ordered pair, but you can't say what is the first ordered pair, what is the second ordered pair. You know what I'm saying. So it can be 3A, 1A, in any order you can write it. So it's a set. But each element is an ordered pair where first element belongs to A, second element belongs to B. Now you may be thinking that what is the use of it? What is the use of this product of sets? One of the uses in the combinatorics actually, the multiplication rule that I will see very soon. The multiplication rule, the ways of doing things if you want to accomplish a task, and that basically There's task T that you want to accomplish, but accomplishing task T means that doing T1 and T2. And let's say there are m ways of doing T1 and there are n ways of doing T2. Then how many ways you can do the task T? Okay. Should I explain multiplication rule right here? See, if let's say you have to accomplish a task T, and to complete task T means doing task 1 and task 2 both, and task 1, for doing task 1, you can do it in m ways. Okay, let's say x1 is one of the way you can do, x2 is another way you can do, and so on so on. There are m ways to perform task 1, and there are n ways to perform task 2. Okay, n ways to perform task 2. Then if you, let's say, if you take any ordered pair means that first element of this ordered pair has to be from T1, and second element from the ordered pair has to be from T2. Then any ordered pair is one way of doing T. Any ordered pair is one way of doing T, right? So if you take x1 y1, I don't know if it is visible or not. So x1 y1 is one way of doing it. X2 x1 y2 is another way of doing it. Another way of doing it. Okay. So in multiplication rule says that if the number of elements in T1 is m and number of elements in T2 is n, then number of ways of doing T is m into n. This is a multiplication rule, because how many ordered pairs you will get is actually m into n. So number of ways of doing T is number of ordered pairs. Okay. And I am taking the ways, T1 to be a set. Okay, this is the fundamental of multiplication. T1, you can think of T1 as a set where each element is distinct way of performing T1, and T2 as a set means task T2. You can think of it as a set where each element is a distinct way to perform T2, and number of ways to perform T is the ordered pair between T1 and T2, ordered pair of T1 cross T2. Okay, number of ordered pairs of T1 cross T2. Okay, I will cover multiplication rule again separately. Just showing that how where it is applied. Actually, this is a fundamental rule of counting. There are two fundamental rule of counting: the sum principle and multiplication principle. Here, the constant is that for t to accomplish, both has to be performed in a sequence. Okay, in a sequence. First T1 has to be performed, and then T2 has to be performed. The sequence can change. Let's say there is another task T dash. For T dash, T2 has to be performed first and T1 has to be performed first. The number of ways would not change to perform. Then the number of ways for T to complete T1, T dash or T is same. That is m into n, because multiplication is commutative. But the ordered pairs will not be same. Ordered pairs will not be same. Okay, in to accomplish. So tell me, what are the ways to do T dash? The ways to do T dash would be now y1 x1, this is one way, y1 x2, this is another way, in this manner. Anyways, multiplication rule is not to be covered here. That's a separate topic of in combinatorics. Similarly, there is a sum rule. In sum rule, we will see how the union operation of set comes into play. Okay, so set is, that's why in the very first introduction to a set, I told you that the sets are very important, because building upon set theory, other concepts are derived, and set is very fundamental. Just think about what is a set. It's just a collection. So collection is a very fundamental thing. Anything, anywhere there is a collection, you can think in terms of set perspective. TOC is completely uh, like set membership. TOC can be summed up as a set membership problem. Anyways, so this is your A cross B. What about if there are three sets? What is the product? We are talking about product of sets. This is a product of two set is set of all possible ordered pairs. But what if you have three sets? What if you have A cross B cross C? A cross B cross C. Then this is a set of all possible ordered pairs. No, it is not pairs anymore. Means it's a set of an ordered entity, but that entity is a ordered tuple, three tuple. Actually, the ordered pairs means these ordered pairs are two tuple. You can think what is a tuple now. Right now, I will also relate it with relational database. So in database, there are different types of database, but relational database is when you are storing your data as a relation, which is actually a table, and each row is called as a tuple. But each row can be thought of, means it is based relational database is based upon the concept of relation only, and each tuple is actually a k tuple. For example, okay, before I explain, let me just write is a set of all possible three tuple, and I will explain what is a tuple. Okay, so let's see a case of a relational database or relation. If you are very new to the computer science and database is something that you have never heard of, then also you can understand it. Database is a uh, record keeping of entities, like, let's say, look at it. Let's say there is a university, and university is keeping a record of students. Okay, keeping a record of students. Then every student must have some student ID. It's like a register. Student ID, student name. Okay, subjects. Okay, so student ID, let's say first student is Gulam. Okay, and he studies subjects. The subject that he studies is computer science and engineering. And second student name is Moinuddin. Okay, and he studies, let's say, machine learning. Okay, machine learning comes under computer science. Artificial intelligence also comes under computer science. Okay, he is a master of physics. And there is a third student. Let's say his name is Ramesh, and he is a master of mathematics. Oh, sorry, he is a student of mathematics. Okay, and grade is that they are all are toppers, always A plus, A plus, A plus. Okay, so in this case, every row, each row is information about one entity, which entity is a student. So one row contains all the information about Gulam, all the information about this student. Second row consists of all the information about Moinuddin. Third row consists of all the information about Ramesh. And each row is called as tuple. Each row is called as tuple because it's an ordered quantity. Means the first element of this tuple is a number that indicates student ID. But if you just take out the tuple out, if you just take the tuple out, then first element has to be a number. Second element is a string, which is a name of the student. Third element is a string, which is a student subject. Fourth element is a okay. हटा दो, प्लस हटा दो, यही लिख दो, आउटस्टैंडिंग कर दो इसको, ओ ग्रेड। थर्ड, fourth element of this tuple is a grade. So this is a four tuple, this is a four tuple, something like this, 1 2 3 4. Then you say it's a four tuple if the order is important in this collection, then it's a tuple. So A cross B is set of all possible two tuples. Okay, set of all possible two tuples, where so two tuples means ordered pair. The first element belongs always has to be from A, second element always has to be from B. Similarly, in this case, A cross B cross C, the first, this is a set of all possible three tuple. Three tuple means the you had three elements in a tuple where the first element always has to belong to A, second element always belongs to B, and third element has to belong to C. And all such tuples possible is your in your product of sets you have all such three tuples. Okay, in database, when I will start, I will again explain this. So you can think in database also, each of this is called attribute. Okay, that student id is one attribute of the student. So this is your student table, this is your student table. Then each of these is one attribute, is the attribute of a student. So you can think of every attribute as a set. Then there is something called as domain, that this set will have a domain. Okay, the content of your table is going to be a subset of cross product of each of this set. Means all of these elements are tuples and they are a subset of cross product of these sets. A set student id set cross student name set, cross product with subjects, cross product with grade. Okay, let's complete this set of product of three sets. So this is equal to nothing but x, y, and z, such that x belongs to A, y belongs to B, and z belongs to C. Okay, so let me take one example to explain. Let's take A to be 1 and 2, A and B, and let's take C to be P and Q. Okay, you will see that the number of elements in A cross B cross C is going to be 8. Actually, the number of elements, the cardinality of A cross B cross C is equal to cardinality of A into cardinality of B into cardinality of C. Every element of A, all possible pair. So for A will be connected with, one will be connected with A, then A with P and A with Q. So one A and P is one three tuple, and then one A and Q is another three tuple. Similarly, one will be connected with B and B will be connected with P and Q. Another two three tuples are 1 B and P, 1 B and Q. Likewise for 2. Okay, so 2A and P, 2A and Q, 2B and P, 2B and Q. Okay. So as you can count the number of elements, 1 2 3 4 5 6 7 8. So this is equal to number of elements in A is 2 into 2 into 2, which is equal to 8. So in general, so I have taken two cases, product of two sets, and I have shown that product of two sets is a set of all possible ordered pairs, which is a set of all possible two tuples. Product of three sets is set of all possible three tuples. Similarly, you can, let's say there are k sets. Then product of k sets is what? Set of all possible k tuples. Okay. And what is the number of elements in the product of k sets? It is equal to the cardinality of each set product of the cardinality of each sets. So when we have product of sets, the cardinality of the product of set is equal to just product of their individual cardinalities. I don't have to. I don't think it needs a proof. It's a straight. But let me show it. Let's take only. Let's take first two sets, and it will be easy for me to explain. Let's take two sets A and B. What is happening is that if this is your set A and this is your set B, then every element of set A is connected with every element of set B, right? So if let's say set B has m elements, n elements, let's say set B has n elements, then A has m elements. Then for every element of A in the ordered pair, in the set of all ordered pairs, each element is each element of A is adding n elements. Okay, each element of A is adding n elements. So this is your first element, let's say A1. So A1 is adding n elements to the set of ordered pairs. M elements, sorry. Similarly, A2 will add, because then now A2 will be connected with each element of B. So A2 will also add n elements, and so on. All the m elements are going to add n elements. So what is the ordered pair? It is n plus so on m times, which is equal to n into m. Okay, which is equal to m into n. Now, if there are three sets, if there are three sets, let's say there is another set A, B, and C, and C has, let's say, p elements. Now, your three tuple, your three tuple is going to be something like this, where these two, this is the this place is for element of A, this is place is for element of B, and this place is for element of C. Now you know that you already know that set of all possible ordered pairs means this part is going to be m into n. Let me just replace it with m into n. What I mean is that this is my A cross B. Okay, so of course this is going to be, let's say, one ordered pair A1 A2 and A1 A1 B1 A2 B1 A2 B2. Okay, don't take it as a set. Why I'm doing so? Because then it will, I will explain in a while that why I'm not doing it. I am just saying that your triplet is going to be like this: A1 B1 and something from set C, A2 B2 and something from set C, A3 B3 and something from set C, and so on, so on. How many such is possible? Means I am not filling this part. I am just looking for distinct these. So how many such? There are m into n such, right? Now to include this, we have to pick it from here, and for each of this, you have p choices. You have p choices. So it becomes in a similar manner. It becomes what? For first one, you have p choice. For second one, you have p choice, and so on, so on. For m into nth one, you have p choice. So the number of elements become what? P plus, so on, p, which is equal to m into n into p. Okay. What about the product of four sets? Similarly, for product of four sets, what you will do? So for four sets, this is like principle of mathematical induction. If you were studious in your 11th and 12th, you would have understood this already, that we can apply mathematical induction to get the result. But I don't think that you were studious, just like me. So if it was four sets, then you know that there's going to be four tuple. There's going to be four tuple. Okay. So you know about, if you just take uh, if you just consider this region up to this, all the distinct elements in up to first three only, then you know that how many are those? M into n into p. And then for each such m into n into p, you have, let's say, for if you have a into b into c into d, if you have four sets, and let's say d has cardinality d, then for each such you have d choices, and then the cardinality of a cross b cross c cross d is nothing but m into n into p into d. Okay, so it's okay. Now let me just directly write. I have proven. So let's say if you have set A1, set A2, set A3, so on, set AK. Okay, then this is the product of such sets. What is the cardinality of this? This is equal to cardinality of A1 into cardinality of A2 into cardinality of A3 into cardinality of A4 into so on, cardinality of AK. This is the result. Okay, so product of sets is over. Let's get little bit about Cartesian product of sets. Actually, when you have only two sets, the product of two sets is also called as Cartesian product of sets. Why? Because think of Cartesian plane. Okay, let me explain. Cartesian product of sets. Cartesian product of A and B. It is just the product of two sets is also called Cartesian product, because you can represent the product of two sets in a Cartesian plane like this. Let's say this is one Cartesian plane. Okay, and this axis is your A, and this axis is your B. Means this axis will have elements of A, and this axis will have elements of B. Okay, let me take just A to be 1 3 5 and B to be 2 4 9. Then what is A cross B? How many elements will be there in A cross B? 3 into 3, 9 elements. So the number of elements in A cross B is equal to 1 and 3, sorry, 1 and 2, 1 and 4, 1 and 9, 3 and 2, 3 and 4, 3 and 9, 5 and 2, 5 and 4, 5 and 9. So this is 1, this is 3, and this is 5, And what are the elements in B? Elements in B is 2, let's say this is 4, and let's say this is 9. Okay, then you just plot it. You just plot it. So with 1, because we are talking okay, this is Cartesian product, so it is all possible pairs. So 1 and 2 will be each, everyone will have a point. So everywhere you will have a point, everywhere. Similarly for 3, so this is something, the Cartesian product will be something like this only, because it is all possible pairs. Okay, in the next video we will read about relation. Relation is a relation is a subset of Cartesian product of sets. I will explain what relation is, but it's a subset. So subset means that some of the elements might be missing. Okay, even the Cartesian product of sets is also a relation. You know, the product of set, Cartesian product of set is also a relation, because every set, one of the subset of any set is a set itself. So this is also one of the relation. A cross B is also one of the relation, but relation is actually can be the proper subset also. So some of the, let's say that if you miss this point or this point, this is one of the relation. So this is the difference between Cartesian product of sets and relation, is that in product of set, the dot will be or every possible dot, and in relation some of the dots will be missing, some of the dots may miss. In the next video we'll talk about relation. Thank you very much. In this video I'll start relation. So what is the relation between two sets A and B? So let's say there is a relation R between set A to B. Okay, so any relation between two sets is a set of ordered pairs. Okay, any relation R between two sets, say A and B, are a set of ordered pairs formed from set of ordered pairs formed from elements of A and elements of B, and elements of B. Like for example, let's say just I am taking just one arbitrary set A that has the elements 1, 2 and 3. Okay, and there is another set B that has the elements as ABC, ABC, and I am just taking one set which is a set of some ordered pairs where the first element belongs to A and the second element belongs to B. Let's say 1A and 1C, 2C, 3B. Let's say I have taken this set. Then this set is what? This set is said to be a relation. We know that A cross B is the set of all possible ordered pairs between A and B. So any relation is a subset of the cross product of set. Any relation is a subset of cross product of sets, cross product of A cross B. So any relation between A to B, this is how we represent a relation, that R is a relation from A to B. So if R is a relation from A to B, then it is a subset of A cross B. Because if it's a relation, then the elements in the relation is going to be an ordered pairs. And A cross B, the elements are all possible ordered pairs. So anyways, you can think of, the analogy in the world of ordered pairs, set of all possible ordered pairs is A cross B. So you can think of A cross B as a universal set. In this context means in the context of ordered pairs, A cross B is a universal set. What is a universal set? The set that has all the elements in a given context. So in this context of ordered pairs, what is the universal set? A cross B. So universal set is A cross B. Okay, so any other set which whose elements are the ordered pairs only, they are called relation. So any relation, the elements of a relation will come from the A cross B only. That's why any relation from A to B is a subset of A cross B. So the definition of relation that I have written here is a relation R, a relation R between two sets are set of ordered pairs formed from elements of A and elements of B, right? Set of ordered pairs. So A cross B itself is one relation only, because A cross B is also a set of ordered pairs. It just happens that it has set of all possible ordered pairs, but ultimately because it's a set of ordered pairs, so even the cross product is also a relation. Okay, A cross B is also a relation. A cross B is also a relation. How do we take these ordered pairs in a relation? Means if 1 comma A is, if 1 comma A belongs to R1, okay, what does it mean? It means that 1 is R related with A. 1 is R related with A. So a relation from A to B means that how the elements of A is related with the elements of B. So in this relation R1, 1A, 1C, 2C, 3B, how set A, how the elements of set A are related with elements of set B. So 1 is related with A. Okay, 1 is related with C. 2 is related with C. 3 is related with B. Okay, you can also think of the relation R as some sort of a rule. How you will relate A and B? Are going to relate it by rule R1. Okay, so by this rule R1, what are the elements that are related? 1 is related to A. 1 is R1 related to A. Okay, 1 is R1 related with C. So by R1 rule, 1 is not related to B. So 1 comma B, 1 comma B does not belongs to R1, or 1 is not related, is not R1 related with B. Okay, how do you represent a relation? This is one way to represent a relation, that you write all those ordered pairs, uh, all those valid ordered pairs, or you can represent it in this manner. This is the diagrammatic representation. Okay, the another way to represent is using a matrix. Also we can represent a relation. Now if 1 is related with A, if 1 is R1 related with A, then I write 1, and if it is not related, then I write 0. So 1 is related with A, then 1. If it's not related, then 0. 1 is related with C, yes, so it's 1. 2 is related with C. 3 is related with B. Okay, so this is about relation. Thank you. Now in this video I'll start functions. So function is a special type of relation where each element of A has to be mapped, and it is mapped uniquely to any other element of B. So let's say any function f or any relation f, for now let's call it a relation f from A to B. Okay, just think about what you know about a relation. In a relation, what happens is that the elements of A is related to elements of B. Okay, and they are relation is any set that has the ordered pair, where the first element is from set A and the second element is from set B, and we call it as it's a relation from set A to set B, like which element of A is related to which elements of B. So if you have this set A and set B, then in your relation, maybe for any element, what are the possibilities? Maybe if you take up this element, let's say I am taking this element, what are the possibilities? It may not form an ordered pair. Okay, so this element may not form an ordered pair. This is one possibility. The other possibility is that it may form an ordered pair. Okay, the other possibility is that it may form multiple ordered pairs. These are the possibilities. Now in functions, it's a special type of relation. A special type of relation in which every element of A must form an ordered pair. Number one, it must form an ordered pair. And number two, it must form an ordered pair with exactly one of the elements from B. So it cannot you cannot have multiple lines going out. It means using this representation, you cannot have multiple lines going out. If f is a function, then if f is a function, so how I'm writing a relation, a function is a special relation in which every element of A is uniquely mapped to an element with B, element of B. So f is from A to B is a function. So when do we say a relation is a function? Means, so if f from A to B is a function, means that every element of A is uniquely mapped to a element of B. Okay, so there exactly one line will go from A to B. Similarly, for this, you can go one line here. Similarly, this can be related to this. But just from A side, if you see, just from A side, there cannot be any element that has no image. Number one. So this also must have an image. Number one point. Number two point, you will not, in this representation, it cannot happen that there are more than one line that is or emanating from any element. The reason being that is this has to be mapped to exactly one, uniquely mapped. Okay, now I wanted to cover a lot of things in function in this just one video, but my board is not functioning well. I cannot wipe out. It's not working. So next video. Thank you very much. Now in this video, let's look at the mappings possible in a function. So let's look at functions mappings. So we know that if function f is from A to B, okay, then if this is your set A and this is your set B, and for any element of A, there's going to be exactly one exactly one image. Exactly every element is uniquely mapped. So from any element, there's exactly one that will go out of it. In this representation. Now They may, let's say this goes to one element of B. Now, all these lines may go to different elements of B. So from A perspective, what is the case? From A perspective, from every element, there will be one map. It will be mapped to exactly one element. So there will be one edge that is coming out from every element from his perspective. Now many of these edges, they may go to different elements of B, or some of these edges may go to the same element. Right? Some of these edges may go to same element. So what is this type of mapping? This type of mapping is called many to one mapping. Many to one from A to B. So from A to B, it is many to one. Like why it is called many to one? Because as you can see, if this is, let's say, this is A1, A2, A3, A4, A5. This is B1, B2, B3. Then many elements of A, that is A3, A4 and A5, many elements of A is mapped to one element of B. That is why it is called many to one. Okay, but let's say if I take a subset of A, let's say any other set S, which is a subset of A, okay, that has elements A1, A2 and A3 only. So let's say F is from, it is just, and how they are uniquely mapped? By rule F only, but the set is S to B, and S has only A1, A2, A3. A1, A2, A3. And this is your B, this is your A. Now, this is B1, this is B2, this is B3. Now, what will be the mapping if the rule is F only? So A1 is mapped to B1, A2 is mapped to B2, and A3 is mapped to B3. This type of mapping of a function is called one-to-one mapping. Okay, in this case, every element of A is mapped to, oh, I'm sorry, this is S. Okay. In this case, every element of S is mapped to a different element of B. So this is called one-to-one. One-to-one. So one-to-one means every element in domain is mapped to different elements in codomain. Different elements in codomain. We have seen about what is a relation and what is inverse of a relation. Okay, inverse of a relation is nothing but when the elements of B become the first element in the ordered pair. So when, if F is from A to B, I'm talking, this is a function, but if any relation is R is from A to B, then R inverse is from B to A. Right? We know that. And R inverse is from B to A, and the ordered pairs of R inverse is just the you just have to swap the positions of the ordered pairs of R, and you get the inverse of the relation. Now, if I ask you that what is the inverse of a function, then inverse of a function is not always possible. For example, consider a many to one function. If I ask you what is the inverse, then if it is many to one, you will find an element in B that has more than one pre-image. In a function F, B3 has more than one pre-image. So when you try to find out F inverse, then in that F inverse, you will have B3 and A3, B3 and A4. So more than one image of B3, this is no longer a function. Function has a function. In functions, the domain is uniquely mapped. So in for many to one function, what we say is that the inverse does not exist. In other words, this is how I have understood. I understand it this way, that if you try to find inverse, you will get a relation but not a function. Okay, but when we are just looking at functions as a topic, exclusively just a function, then we don't say that inverse is not a function but it's a relation. We generally talk whether inverse exists or not. So because the inverse will have multiple image for a given element, we say that the inverse is not a function, so inverse does not exist. Okay, many to one function is not invertible. In this case, if you try to find the inverse, what will be f inverse? So f inverse is from B to S, and f inverse is equal to B1 A1, B2 A2, and B3 A3. Okay, so f inverse exists for this one-to-one function. Let me tell you that f for a inverse to exist, it has to be one-to-one, but not only one-to-one. In this case, your codomain is your range. In functions, I don't know if I have talked about what is range or domain. Domain is your set A, and codomain is your set B. Domain is your set A, codomain is your set B. Okay, and those one function are invertible, which is also onto functions. What is onto function? Okay, so far you know what is many to one, what is one to one. Now let me tell you that a rule is from set A to set B. F is a mapping from set A to set B. Set A is called domain, set B is called codomain. Okay, so from set A, each and every element is uniquely mapped in a function. And when it comes to set B, how can you look at any element of set B? Means what is the possibilities of any element of set B? Either it is mapped or it is not mapped. If it is mapped, it may be mapped to single element, it may be mapped to many elements, or there may be some elements that do not have any pre-image. It is possible. Let's say if it is not B, let's say when we are talking about B dash is another set, and it has other B4 and B5 elements also. Now if you look at B dash, then what you will say is that in this case, not all the elements have a pre-image. Okay, so B dash is codomain. And what is range of a function? Range of a function is those elements of codomain that has a pre-image. That is called range. Based on the range, you have two types of functions: onto function and into function. If all the elements have pre-image, then range is equal to codomain. Or maybe some of the elements do not have pre-image, like B4 and B5. Look at this: B1, B2, B3. For this set B, all of them have a pre-image. So the codomain is also the range. Range is also the codomain. Range is equal to codomain. Here, your range is a subset of codomain. So your range is always going to be Range is always going to be a subset of codomain. Okay. When range is equal to codomain, we call it as onto function. And into is when range is a proper subset of codomain. Means that you will find some element that do not have any pre-image. Now let's say f is from f to b dash. Now you have b4 here and b5 here. Now does inverse exist? Now inverse do not exist. Why? Because when you try to find f inverse, you will get b1 a1, b2 a2, b3 a3. So the images that you are getting, this is one-to-one map, no doubt. But for b4, b5, there is no image. But the definition of function requires every element to be uniquely mapped. So for if so only functions which are 1 1 and on 2, they are invertible. This function is not invertible. So only 1 1 and on 2, 1 1 and on 2 functions are invertible. Only 1 1 and on 2 functions are invertible. 1 1 and on 2 functions, those functions which are 1 1 and on 2, they are called bijection. Means 1 1 and on 2 together. When any function is 1 1 also and on 2 functions, those functions we call it as bijection. Bijection. And so only bijections are invertible. Bijective functions are only bijective functions are invertible. Okay. So these are different mappings in a function, many to one and one to one. Are there any other possible mappings? No. The reason is very simple, because just look from A. From every element, only one edge can come out, right? Only one edge can come out. Now these edges may go to different elements. All the edges may go to different elements. Okay, then it will become one to one. Or maybe some of the edges are going to just one element. Maybe some of the edges go to same element. If some of the edges go to same element, then we call it many to one. So there is no other mappings possible. Now this mapping that we are saying many to one, this is from A to B. So from A, many elements of A may be mapped to one element. So if in your mappings there exists some elements, if in your mapping there exists some elements that are mapped to same element, then it is many to one. And if in your mapping all the elements are of S, or all the elements of domain is mapped to different elements of uh, codomain, then it is a one-to-one mapping. So how do you prove if a given function is one-one function or many-one function? How do you prove it? Now for one-one function, if A is not equal to B, if A is not equal to B, then f of A is not equal to f of B. Is this not the case? By the definition of one function, for any two different element, if we know that it's two different element, then their image must also be two different elements. So for one function, if A is not equal to B, then f of A is not equal to f of B, right? So how do you prove a function to be a one function is, you assume that A and B are two different elements. Okay, you suppose that you take any two arbitrary elements and you assume them to be different. Suppose A not equal to B, and you try to show that f of A is equal to f of B. Then solving this will ultimately give you what? That A is equal to B. If this happens, it means what? It means the function is 1 1. What I mean to say is that if you want to prove any given function is 1 1 or not, how do you do it? Let's say if f of x, so polynomial functions, they are 1 function. Okay, let's suppose a polynomial of degree 1, y is equal to ax plus b form. Let's say y is equal to 3x plus 5. Now we say that this is 1 1. It is very clear that this is 1 1, and this is also one of the tests. If the graph of the function is given, then you can find how, if it is many 1 or 1 1. So it's very easy. Just This is, I will explain it again, but I'm removing this. Okay. If you have to know if it's a function, relation, or function, if it's a relation or function, how do you find it? How do you find if it's a relation or function? This idea of a function where f is a rule, f is a rule by which you map, rule by which elements of domain is mapped to codomain. Elements of domain is mapped to codomain. Okay, input is taken from the set domain, and the output belongs to one of the elements, belongs to any one element of the codomain. Now, we represent y to be equal to f of x. F of x. What does this mean? It means that to your function, your input is x. When your input is x, it is like a machine. When you give some input, it will give some output by applying a rule on this input. Okay, say f is a function from real number to real number such that the mapping is twice the number. Like if f2 is here, then you will get 4 as y. Means when x is 2, then y is 4. This is your input to the function and this is your output to the function. Similarly, when x is 4, then y is 8. Look carefully, I have taken domain to be set of real number and range to be codomain to be set of real numbers. Okay, now what happens is, so what is this rule? You can say that a rule is your f is an expression with respect to the input variable. Knowing this expression means you know the function. Knowing the expression means you know what the function is. So in this case, you can say that f of x is equal to 2x. So when you know what x is, you use this expression to get the value of y. That's why I have written here y to be equal to f of x. F of x is an expression with respect to the input. Okay. Now you know that in relation also we have seen many different representations show the mappings in this manner. One another representation we have seen is that of a Cartesian plane. On x-axis you have elements that come in your as your first ordered pair or elements of set A on the x-axis. In case of relation, you have elements of set A on x-axis and elements of set B. Means if your relation R is from A to B, then in your Cartesian plane representation, elements of set A is on x-axis, elements of A on x-axis, and elements of B on y-axis, and then any point on that xy plane will represent an ordered pair of your relation R. If let's say if this is some b1 and this is a1, and let's say a1 b1 is a1 b1 belongs to R, you will mark it. But if let's say a1 b2 is not, a1 b2 is not an ordered pair, then you leave this position as it is. You don't mark it as. So this is how your relation is plotted on your Cartesian plane. Now in case of function, your domain is on x-axis and your codomain is on y-axis. Function is from A to B, then these A's, elements of A, that is the elements of domain on x-axis and elements of codomain on y-axis. This is by convention. Okay, look at here. This is your x-axis. Okay, this is your x-axis and this is your y-axis. This is 1, then this is the mapping is, so this value is nothing but 1 and 2. So this is 2 on your axis. Similarly, this is 2, let's say, then this will be 4. This is 2, then this will be 4. Okay, let's say this is 3, then the corresponding value, this one, is nothing but 6. This is 3 and 6. This is 2 and 4. This point is 2 and 4. Okay, so that's how the graph of a function is. If the graph is given, I mean, look at this, f(x) is equal to 2x. This is an expression, 2x, where x is an input. This is one expression. From this expression, can you guarantee that this is a function? Just from an expression, can you guarantee that this is a function? Of course not. Of course not. In this case only, if you see f is from R to R, let's say if I make R the codomain to be only up to 6, you can't say that this is a point for 4 and 8 is a part of your function, that you give an input 4 and you will get an output 8. No, because your codomain, I am limiting your codomain from 0 to 6 only. So 4, 5, 6, whatever comes after 3, all of them do not have an image, and so this f is equal to 2x is not even a function. If I limit the codomain to be from 0 to 6, then this f is not a function anymore. Just by looking at the graph, you have to know if it is a function or not, because definitely it's a relation. If there is ordered pair, here you have ordered pair, means that it's a relation. But if this relation is a function or not, if you have to guess that, then you know what the definition of a function is, and based on that you can find it out. This is what your function is. Now in this you have two component. Let's say in this you have two component, all elements uniquely mapped. If your codomain is 0 to 6, then from 4 onwards, f(x) is equal to 2x is not a function, because 4, 5, 6, so on, they are not having any image in it. Okay, one more thing. I've been taking only natural numbers as x, however it is r, but as you can see, uh, even you can take 2.1, then y would be 4.2. okay, you can see it's a continuous graph. So for every element in x, for every point in x, you have an image up to 3. If your codomain is 0 to 6, then up to 3 you have. For every point from 0 to 3, it is, you will say that it's uniquely mapped. But from 3 not included, to infinity, it's not mapped. No mapping. So it is not a function. Okay, but if your f is from R to R, then it is a function clearly, because for every input you are getting a unique output. For every input, if you see 4, then for 4 you get a unique output, that is 8. This is 4,8. For 5 you get a unique output, that is 5,10. So for every element you have a unique output. So it is a all elements are uniquely mapped, so it is a f of x is equal to 2x. F of x is equal to 2x, where f is from R to R is a function. If your domain is on the x-axis and you want to look if this point, any point is uniquely mapped or not, how do you find it? How do you find that what is corresponding to what is y corresponding to x? You are drawing a line that is parallel to your y-axis from that point of x. So for any x, if you want to find its image, you are drawing a line parallel to the y-axis, and wherever it will cut the curve, that will be its image. So when do you say that this curve is that of a function? For all the points in the domain, when you draw a line perpendicular to x-axis from that point, from all, okay, if you draw a line perpendicular to x-axis for every point of domain, and it cuts the curve, and that perpendicular line cuts the curve at exactly one point, then it's a function. Okay, now if you find, if there exists any line, any perpendicular line, if there exists any perpendicular line from any point in the domain, that cuts your curve at more than one point, or do not cut the curve, that cuts your curve at more than one point, or do not cut the curve at all, this is not a curve of a function. Of course it's a relation, but it's not a function. Now you know if a curve is given, how to know if it is a function or not. Now then the second thing is, you know there are two types of function, one function and many one function. Given the curve of a function, how do you determine if it is one or many one? In case of one and many one, look at it from the codomain elements of codomain perspective. Then if you take any element, then what are the possibilities for this element? Either it is the case that if it is one, then it may not have any preimage, or it may have one preimage exactly, but not more than one. So for a one function, every element of a codomain has at most one preimage, right? So for one, every element of codomain has at most one preimage. Codomain is on your y-axis, so these are every point on your codomain. If for any element you draw a line parallel to the x-axis from that point, so parallel line to x-axis, you get this point. What does this point means with respect to this point? It means this is your pre-image. If this is your y1, then this is x1 y1 point, this point is x1 y1, then the x1 is the pre-image of y1. So you, if it is a 1 1 function, then if you draw any line, in this case this is also a onto function because f is from r to r and y is equal to 2x, this is an onto function. So for every element in y also you have a pre-image, that is y by 2. So the test for 1 1 from every point, from every point on codomain, from every point on codomain of y-axis, a line perpendicular to y-axis, or you may say the parallel to x-axis. So from every point, if from every point, if from every point on codomain of y-axis, a line perpendicular to y-axis cuts the curve at most one point, at most one point, then this is uh, 1 1, then this is 1 1. Okay, test for any one point that cuts it at more than one place. If there exists a point on codomain such that perpendicular line through it, perpendicular line to y-axis through it, through this point, cuts the curve at more than one point, cuts the curve at more than one point, then it's many one, then it is many one. Based on the type of mapping, you have 1 1 function or many one function, but based on your range and codomain, what will be the test for onto and into? For every point of codomain on y-axis, you draw a line parallel, okay, then wherever it cuts the curve, that is your pre-image for that codomain element, right? Now it will be onto if for all points it cuts the curve. If you want to know if it is onto or not, what do you want to show? You want to show that every element of codomain has a pre-image. So for every point, if I have to write it onto onto, just for a moment think about this, that this is a test for onto. Then if from every point on codomain of y-axis, a line perpendicular to y-axis cuts the curve, that's it. If it from every point, if it cuts the curve, here I am writing at most one point, so it may not also cut for 1 1, I don't care, but if it is onto, then it must cut the curve. So what will be the case if it is 1 1 and onto? It means that for 1 1 and onto, every point on codomain of y-axis, a line perpendicular to y-axis will cut the curve at exactly one point. For all such points, it will cut at exactly one point. If I am looking to get if it is into or onto, I am just seeing for all such points, if there exists any point, for which it does not cut the curve, it means it is into. Okay, so that's it. Okay, let's take just one example. Is this many one or 1 1? If you take up this y, then it cuts the curve at this point, and this point. It means if this is, let's say if this is x1 and this is x2, then this point, and this is, let's say, y1, then this point is x2 y1 and this point is x1 y1. So this is many one. How? Because y1 has two pre-image. So it is like this. Here you have x1 and this is your y1 and this is your x2. X1 is mapped to y1 and x2 is mapped to y1. So this is many. Okay. If all lines parallel to y-axis uh, cuts at exactly one point, then it's a function. Now, okay, to be very precise, okay, I assume that the curve is only up to the domain. So I am assuming that if let's say this is your domain, region of domain, I'm just looking up to this area and then it will perfectly fit and the definition will perfectly fit. I'm not going to draw any line parallel outside of this domain. Okay, whatever definition I'm writing here, that is very much precise definition. The assumptions is that I am drawing it within the domain, and similarly for horizontal parallel line, the assumption is that I'm drawing that horizontal line within the domain section or domain interval. So if all line parallel to y-axis cuts at exactly one point, then it's a function. Otherwise, it's a relation. Otherwise, relation. It's just a relation. Okay. And how do you find? So I'm erasing again. So given the curve or graph of a function, so it's known that it's a function. It's known that this curve is of that of a function. Then how do you find if it is many one or not? One or many one? One or many one? For one or many one, if all horizontal, if all lines parallel to x-axis, if all lines parallel to x-axis cuts the graph, cuts the curve at most one place. Why I am writing at most? Means I'm trying to define it for one. So why I'm writing at most? Because maybe there are some elements of codomain that do not have any pre-image. It is possible. So at most one place, then it is one. Then it is one. So one means for different elements, different image. Now, if there exists a line, there exists. If there exists a line, if there exists a line parallel to x-axis, parallel to x-axis, which cuts the curve at more than one place, which cuts the curve at more than one place, it is many one. Then it is many one. Then it is many one. Now, from range and codomain perspective, if it is onto function or into function. So how can you say if it's onto or into function? So if it is 1 1 and onto means what? It means that all the lines will cut at exactly 1 point. All lines parallel to x-axis. Means if you are taking up any line that is from any codomain, you take up any point in codomain in on y-axis, any point, then it will cut it exactly 1 point. Meaning to say, I just want for every point, I just want a pre-image. So if all lines parallel to x-axis cuts the curve at exactly one place, then it is 1 1 and only if all the lines parallel to x-axis cuts the curve, then it is minimum. Then it is onto. Otherwise, into. Okay, let me give it for onto and into also. Let me do it separately. Onto and into function. So given a curve of a function, if it is onto or into, how do you find? If all lines parallel to x-axis cuts the curve. Cuts the curve. So if all lines parallel to x-axis cuts the curve, then onto. If there exists a line, if there exists a line parallel to x-axis, if there exists a line parallel to x-axis that don't cut the curve, that doesn't cut the curve, that doesn't cut the curve, then into. Then into. The video is getting long, so there are other things that I wanted to cover in the same video, but it will be covered in the subsequent videos. So I will continue this function mapping in the next video, and I will describe this in more details with more such with more formulations, and then maybe in the next video or maybe in the next to next video, we will see that what types of mappings are possible in a relation. Thank you very much. So in the last video, we have seen that in functions, the mappings are either 1 1 or many 1. So if some of the elements of the domain, if they get uniquely mapped to one element, one common element, then it's a many 1. And if all the elements of domain are mapped to different elements of codomain, then it's 1 1. Now let's look further into it. Let's say you have a function from a to b. Okay, this is 1 1 function. Okay, now if it is 1 1, if it is 1 1, it means every element of a is mapped to different elements of b. Okay, so if it is 1 1, let's say the number of elements in a is equal to n, then what should be the number of elements in b? Because every element of a is mapped to a different element of b. If this is your a1 and this is your a2, a1 is not equal to a2 means that f of a1 is not equal to f of a2, right? If a1 is mapped to, let's say, b1, now b1 cannot have any pre-image other than a1. In your 1 1, from the b's perspective, every element of b will have a unique pre-image if it has a pre-image. Okay, in 1 1, any element of B may or may not have a pre-image. If it has a pre-image, then it's a unique one. So A2 will be mapped to some other element, but not B1, B2. So in this manner, the number of elements in B has to be greater than or equal to A. Means for sure, what is the minimum number of elements in B? If every element is mapped to some other element, every element of A must have an image because A is the domain. And for a function, all the elements of domain have a unique image. So it means the number of elements in B, minimum number of elements in B has to be equal to the number of elements in A. So number of elements in B is greater than equal to number of elements in A, because there might be some more elements, B6, let's say B7, that has no pre-image in A. This is your 1 1. So in case of 1 1, if number of elements of A is n, the number of elements in B is greater than equal to n. Okay, so basically the thing is, in 1 1, number of elements in your codomain is greater than equal to number of elements in your A. Now when this is equal, because it is greater than equal to, so you can divide it, you can take it as two cases. When number of elements in B is equal to number of elements in A, or when number of elements in B is greater than number of elements in A. Okay, so when number of elements in B is greater than number of elements in A, what does it mean? It means there are some elements that don't have any pre-image. It means that your range is a subset of your codomain, proper subset. It means it is into function. It means 1 1 and into. Now, if number of elements in B is equal to number of elements in A, it means that all of those elements have a pre-image, and so range is equal to codomain, and so in this case it is 1 1 and onto. Look at this. A1 is not equal to A2, then f of A1 is not equal to f of A2. This is you can take it as a formal definition for 1 1 function, that when two different elements of A, they have two different their images are also different. Now, if a function is given to you, how do you find out if it's 1 1 or not? Okay, if a function is given to you, how do you find out if it's a 1 1 or not? In the last video, we have seen that if the graph of a function is given or the curve of the function is given, we can easily find out if it is a 1 1 function or if it is mini 1 function. Now, let's say expression of a function is given. Curve is not given, just the expression of a function is given. Then how can you find out if it is 1 1 or not? It's very simple. You make use of this fact that let's say f of x is equal to 2x. So here f is from A to B. Let's take an example where g is from R to R. So we have seen in the last video that how it is a function and it is a 1 1 function. Now if this just the expression is given and curve is not given, just from the expression itself you can find it out, making use of this fact that if you assume f of A1 and f of A2, where A1 is not equal to A2, then both of them have to come different or unequal. Now what you do, you make it equal. You make f of A1 and f of A2 to be equal. So when you make f of A1 or f of A2, so I am erasing this now, 1 1 or not, that is what you have to check. So what you do, you know that in a 1 1 function, A1 is not equal to A2, or simply say A not equal to B. Okay, if A is not equal to B and A and B belongs to the domain, then g of A will be not equal to g of B. This would be the case if it is 1 1. Now, if you want to prove it, then what you do is you you will make you will find GA, you will find GB, and you will equate them. Okay, just do GA equals to GB, and if ultimately solving this gives you A is equal to B, it means what? It means that the expressions are, if the expressions are equal, means the input you give was equal. Okay, otherwise the two will never be equal. This is what will prove that this function is 1 1. So if you do 2a, g of a is 2a and g of b is 2b. So this gives a is equal to b. It means that this was 1 1. I am taking any general, any arbitrary element a and b. Okay, that's it. This is how you can find if a function is 1 1 or not, if the expression of the function is given. So what we can say about 1 1, number one is that if function g is 1 1, means that a not equal to b, then f of a is not equal to f of b. So okay, this time I'm taking g of x, so let's do g of a. Means my function name is g, rule name is g. So if a is not equal to b, then g of a is not equal to g of b. Means if it is known that your g function is 1 1, if it is known that g is 1 1, then if a is not equal to b, then g of a is not equal to g of b. If g of a is equal to g of b, then what you can say? Then it means a is equal to b. I wanted to complete the mapping in this video alone, but right now, biryani. Now that we know what's a 1 1 mapping and many 1 mapping, let's look at the range of the function. So range is the set of those elements in codomain that have a pre-image. Okay, so if it's a 1 1 mapping, so if it is a 1 to 1 mapping, okay, in case of 1 to 1 mapping, uh, if number of elements in A is n, then the number of elements in range is equal to number of elements in A is equal to n. Because for every element in A, the range, each element is mapped to a different element. Each element is uniquely mapped, and these lines goes to different elements in your codomain. So in case of 1 1 function, range is equal to the number of elements in A only. And if it is a many 1 function, if it's a many 1 function, if the number of elements in A is equal to n, then if you just look at from A1, A2, so on, there are many elements. Just looking at A, if it is many 1, what is the smallest number of elements in the range? 1. Because for smallest element, consider this when all the elements are just mapped to one element. Then this is a many 1 function. So in case of many 1 function, the range is greater than equal to 1. Okay. Now, this is when your domain is given to you. Number of elements in domain is given to you. Then what is the number of elements in the range? So in case of 1-1 mapping, if number of elements in A is n, the number of elements in range is n. In case of many one function, if number of elements in A is n, range can be anything greater than equal to 1. Okay, and when range is equal to 1, then it means all the elements are mapped to just one element. Now, what if a range is given to you, and what do you make up about the domain? That is, if range is equal to n, if range is number of elements in range is equal to n, then what does it tell about the number of elements in domain A? Okay, so of course, in case of 1-to-1 function, every range, every element of B that constitutes range, it will have a unique pre-image, and that is, so the number of elements in A is equal to number of elements in range, that is equal to n. And for many one function, what does it mean? It means that number of elements in A, if range is given, what is given to you is range. Okay, what is given to you is range. Range is given, then number of elements in A is this. Now range is n. Range is n means what? Means that the number of elements of domain has to be greater than equal to n. Which means here, if you look, this is B1, let's say, this is your set P, this is your set A. B1 is an element of range. Then it means B1 has a pre-image. It is many one, so maybe it has more than one pre-image, but B1 is a range means B1 has a pre-image. B belongs to range means what? B belongs to range means that B has pre-image. Maybe more than one pre-image. Now it means that if you have any other element B2, let's say any other element B3, and these are your range, these all of them are range, it means they are mapped to some element. Now is it possible that B2 will be matched to A1? No, it will not be a function anymore. So it will not be a function, because if A1 is mapped to B1, then A1 will not be mapped to any other element. So for element B2, B2 will not be mapped to A1 or A2 or AN. B2 has a pre-image A1, it means that A1 has two images. Okay, so for every different element that you see in the range, they confirm what? If B1 has a pre-image, then that pre-image will not have any other image. Means if pre-image of B1 is what? A1, A2 and AN. A1, A2 and AN. Now it means that any other element of range, like let's say pre-image of B2 or pre-image of B3, they will not have A1, A2 or AN, because of the definition of function. It will not remain a function if any other element of range will have the same pre-image as any element. Any two element of range cannot have a common pre-image. Okay, because of the definition of function that elements of A has to be uniquely mapped. So any two element of range cannot have a common pre-image. So because of this, what can you say about the number of elements of A? So number of elements in A is equal to from your range you can find out pre-image of B1 plus pre-image of B2 plus so on so on, pre-image of, let's say, Bm. Okay, number of element in range is n, so let's say it is Bn, where B1, B2, so on Bn, these are range. Okay, so number of elements in range is n, so I'm saying that let range be B1, B2, so on Bn. The number of elements in A is this, and every set of pre-image of B1, set of pre-image of B2, they are disjoint. Any two set is disjoint. So and so what I can say for with surety is that number of elements in A is greater than equal to n, because the minimum, if B1 is a range, then it may have pre-images. So minimum value that any cardinality, minimum value of any of these terms will be 1. It will be greater than or equal to 1, equal to n. So number of elements in A is greater than or equal to n. So I think it's okay for now. In the next video, we will see some different mappings possible in relation. So mapping about function is over. Thank you very much. In the previous videos, we have covered the mappings in a function, and we have seen that for a function, there are two types of mapping, many one and one. And based on the mapping, so we have two types of function, many one function and one function. And this is because very simply, for every element in your domain, or because if your function is from set A to B, then for every, means mapping is from set A to set B, because every element of A is uniquely mapped. There is only one edge that comes out of A, so it might happen that all of them are going to different elements in B, then it is one mapping. And if it happens that you have some of these lines going to the same element, then it is a many one mapping. Now, but when it comes to general relation, just I'm not talking about a special relation of that is function, which is constrained that every element is uniquely mapped. I'm just talking about the general relation R, which is from A to B. From individual element of A, possibilities for any element of A is that it is not mapped at all. That is, it does not contribute in the ordered pair of a relation. This is one of the possibility. Another possibility is that it contributes in the ordered pairs, and it contributes in more than one ordered pair. That is, it is not uniquely mapped. So it may happen, let's say, if this is my set A, then for any arbitrary element, let's say A1, so it might happen that R does not have any ordered pair with A1 as its first element. That is, A1 is not mapped at all. Let's say there's another element A2, and this is uniquely mapped to some element, let's say B2. Then we have an ordered pair like A2, B2. And let's say you have an element A3, and this element may be mapped to multiple elements. Okay, B1, B3, and then this will contribute A3, B1, A3, B2, A3, B3. So when it comes to function relation, a lot of things are possible. Consider A3. There may be lot of such A3s. Means lot of elements in A that have this thing, the multiple lines going out. So it is like if you just take up, let's say if you take up A4 also, and A4 is mapped to B4, B5, B6. B4, B5, B6. So let's take a subset of A, which is just A3 and A4, and B completely. So a subset of A dash, which is A3 and A4. Subset of A dash A3 and A4, and B as it is. A3 is mapped to B1, A3 is mapped to B1, B2, B3, B1, B2, B3. A4 is mapped to B4, B5, B6, B4, B5, B6. So what type of mapping you can say? What type of mapping it is? It is one to many mapping. Okay. Similarly, many to many type of mapping is also possible. Here, one element is mapped to many elements. Many to many means many elements are mapped to many elements. Okay, so there's mapping among many. So it's like a hodgepodge. Everything is possible in a function, in a relation, in a general relation. When it comes to mapping, anything is possible. I have just taken a subset to show you one to many. But in a given relation, when you have many elements in A, let's say A1 to AN, when you have too many elements and everything is going on at the same time, in calculus we just specifically deal with functions. Okay, so from the next video onwards we will see value of the function, limit of a function, because it's function that is uniquely mapped, and because of that uniquely mapped, for a given input you get a particular output. In calculus, we will study things like limits, then continuity, differentiability. Main focus is on optimization, how to know when the function is at the highest value, when it is lowest value. All of those things is because the curve, the nature of the curve of a function is that when you draw a perpendicular line with respect to x-axis, then you are going to cut the curve at only one point. You have a definite value for a given y, for a given x, a definite y. So from next video, we will start calculus. Thank you very much.